All right, welcome everyone to our post-class video, bonus video, if you would, with the problems that didn't have time in class to discuss or solve. And so, wanted to start off with this surface integral with a scalar function. In this case, we are integrating the function, nice boring function y. We have a surface that is given by a z equals surface. And so we're going to be using the explicit formula here. And we have nice bounds. X ranges from 0 to 1, Y ranges from 0 to 2. And so let's go ahead and get started with this. The big thing is converting this ds, right? And in order to do this, we need the square root. We're going to be looking at our surface equation here. After all this s, the surface, right? Is where all this information lies. We need to take a partial derivative of our surface equation here with respect to x, square that. Partial derivative with respect to y, square that. Add on 1, throw those all under a square root, and then you have dA. And this dA, again, the surface is some interesting surface in XYZ space. But now after we've converted from ds to dA, this is just in the xy plane. There's some region in the xy plane. And of course, this is given to us by these nice bounds here, x ranging between 0 and 1, y ranging between 0 and 2. And so if you wanted to sketch that, it would just be a nice rectangle. So this is our region in that xy plane. I shade it in black or so. So all that to say, right, is that it doesn't really matter if we integrate with respect to x first or with respect to y first. I wouldn't recommend using polar in this case. And so let's go ahead and take a line to simplify here. 2 plus 4y squared. I'll do dy dx. Y's range from 0 to 2. X's range from 0 to 1. We can evaluate out our x integral really at any time, just like when we do like r's and thetas and whatnot. We notice that there's no x's here. We have nice constant bounds. And so if you were to separate off to the side here and do an x integral from 0 to 1, well, the integral of x will be x. Evaluate that from 0 to 1. You're just going to have 1 minus 0. So this right here, I'm just going to go ahead and simplify down to 1 minus 0. For the other piece here, we're going to have a small u substitution. So if u is equal to this 2 plus 4y squared, again, I'll just go off to the side here. U is equal to 2 plus 4y squared. Then du is equal to 8y dy. Or another way to say that is that y dy is the same thing as 1/8 of a du. And that's particularly nice because we have a y dy that we can go ahead and trade in for a 1/8 of a du. So now, when we integrate this, well, u to the 1/2 power, that square root of u there, that's going to become u to the 3/2 power multiplied by our 2/3. Double check if you take the derivative of that, you should get back to where you started. Let's go ahead and also swap in, instead of my u, u is the same thing as 2 plus 4y squared. And I remember some time ago in class or whatnot, someone asked me, why am I dividing by stuff? I'm not dividing by stuff, right? I'm just, this is equivalent. So I was just writing that for the u's and the du and whatnot. So this is equivalent to the square root of u times 1/8 du. So again, you can kind of erase that or move it off to the side if you'd prefer. All right, finally, right, I need to evaluate that integral from 0 to 2. And so let's see, there's going to be a little bit of cancellation here. I'm going to have 1/12. And then when I plug in 2, everywhere I see a y, let's say I'm going to have 4 times 4, that would be 16, plus another 2, that's going to be 18 to the 3/2. And when I plug in 0, I don't get out 0, right? I get 2 raised to the 3/2. And so that right there would be my final answer. And so this one right here, I think, is a fine level for a quiz or an exam or something like this, where still does get at the heart of these surface integrals, but you can see that this only took me about 4 lines or so to solve, especially, I mean, if you don't spend too much time on the u substitution. All right, well, that is the last problem that I had for these scalar functions for our surface integrals. Of course, in class, we talked about a couple different situations for flux or surface integrals with vector fields. we had gotten so far as to evaluate out our surface integral on this particular function here on the bottom piece, that is S2, or a portion of the xy plane, aka z equals 0. But we didn't get to evaluating out our surface integral on the first surface, the more interesting one, this paraboloid. And so let's go ahead and spend some time thinking about this. Again, we have some outward orientation. And so you can see that on this surface, right, S1, that this is going to be with a positive z component, right? It's mostly pointing up. Sometimes it's not up by a whole lot, right? Here it's not up by a whole lot, but it is positive. And so when I'm looking at this, we can notice that my z component is relatively nice, right? It's always just a -1. And we have to decide if it should stay as a -1 or if it should be a +1. AKA, we need to choose either a positive or a negative. This is choosing the orientation for the surface. And in our S2, right, we said that we wanted it to be pointing downward, because on this piece here, downward was the same as outward. However, for S1, this more complicated one that we're looking at now in our case, right, we want it to be pointing upward because this one's on top. And so upward is equivalent to outward. And so all that to say is I'm going to choose this extra negative here. So that way, when I distribute to each one of these, right, I get a +1 that's going to be oriented upward. And so let's go ahead and spend some time simplifying this down. So this is going to be, again, let's change all these to positives. So 2x times y is going to be 2xy. And I'm evaluating out my dot product, right? So x times 2y is going to be another 2xy. And then finally, we have this last piece times 1. So +1 minus x squared minus y squared. Now, again, when we've evaluated this out, right, this is dA, we're kind of in the xy plane at this point. And so I need to take my surface, my S1, and I need to smush it down into the xy plane. And so if I was to take this and smush it down into the xy plane, right, it would all lie inside of this circle here. This is actually the same thing as, basically S2. And so we take this in the xy plane. And again, this stops where our paraboloid surface, 1 minus x squared minus y squared, intersects with z equals 0, right? And so this is going to be a circle of radius 1. And so because of that, right, when I'm evaluating out a double integral, just like I did back in chapter 15, I have to decide, do I want to integrate with respect to y first, with respect to x first, or switch into polar? And so because I have integration over a circle, I'm going to switch into polar here. And so let's go ahead. We're going to have 2 plus 2 is 4xy. X is r cosine theta. Y is r sine of theta. And then +1 minus, and x squared plus y squared, right? Once you factor out that negative, that's going to be equivalent to r squared. dr d theta. And then you would yell at me, right? Because I've forgotten my Jacobian. I've forgotten the r. And so even here in chapter 16, right, just like what we did back in chapter 15, whenever you convert into polar, you need to make sure to include in that Jacobian the extra r, so it should be r dr d theta. All right, because we're inside of a circle of radius 1, our r's will range from 0 to 1, and our thetas will range from 0 to 2 pi. All right, so I have the setup all done. Now it's just time to evaluate. Okay, well, I need to evaluate out my r's first, and maybe I can go ahead and take one line to simplify here. Let's see, when I multiply through by this r, I'm going to have, 4, and there's going to be 3 r's in this term altogether, so 4r cubed. I'm just going to kind of rearrange this a little bit to make it nice for me. Plus 1 times r, that's going to be r, and then minus, instead of r here, I'll put r cubed. All right, so there we go. This is kind of just a little bit simplified down. So that way I can just move into my integration now. All right, so when I integrate with respect to r, let's see, still going to have a theta integral. Let me kind of start farther over to the left here, just because I am worried about having enough room. So a little bit farther over here. So I'm going to have r to the 4th, still have all of our theta stuff here, plus 1/2 r squared minus 1/4 r to the 4th. And again, r's range from 0 to 1. Of course, when we plug in 0, we're going to get out 0. And if you plug in 1, you'll just get 1. So there we go. Plus 1/2, and 1 squared is 1, minus 1/4. And there we are. All right. So finally, let's go ahead and evaluate out our theta integral. Now, again, this can be done with a small u substitution. So if like u is equal to sine, then du would be just cosine d theta. And so when I integrate this, this is going to be the same thing as 1/2 u squared. And again, u is equal to sine. So 1/2 sine squared theta. And of course, you can double check, right? If you take the derivative, you should get back to where you started. So this is a correct antiderivative. Plus 1/2 theta minus 1/4 theta, which of course you could have simplified that if you'd like. So now if you plug in either 0 or 2 pi into sine, right, your calculator will verify for you that this is 0 in both of those cases. So this is just going to be equal to 1/2 times 2 pi minus 1/4 times 2 pi. And so again, if you simplified this would be maybe a little bit nicer, whatnot, but either way, you're going to get the final answer of pi over 2. So again, this is going to be pi minus 1/2 of a pi. So that's going to be pi over 2. All right, then I guess finally, right, we found that the surface integral on S1 was pi over 2. We found the surface integral on S2 was 0. So really, in order to get our final answer, we would want to add this pi over 2 to 0. And so we would get our final answer of pi over 2. So on the entire surface, we would get pi over 2. But in this case, right, of course, adding 0 doesn't do a whole lot. So, all right. Now, just as a reminder, right, in the flux definition, we have, right, this is our notation. What this means is that we're doing our vector field and dot producting that with our normal vector and then doing a classic surface integral here. We can interpret this calculation as summing up movement of particles induced by the vector field across the surface S. Hence, right, because we want to go across the surface, we dot product it with the normal vector. Quite often when I'm thinking about flux, I imagine my surface as some like bed sheet, right, that's like hanging in the wind that we've put out to dry or something like this. And maybe the vector field is some velocity field, right? And maybe there's wind blowing, and it could be blowing up, it could be blowing down, right? And you kind of imagine particles going through the bed sheet. Of course, the bed sheet, stops some of them, but there's some flux, there's some movement of particles going through the surface. And so that's kind of what I'm thinking about when I'm often thinking about flux. All right, well, the last problem that I wanted to go over with you guys here is a case where we have a parameterized surface. And so we've seen something close to this, but we want the outward flux for our vector field, z, y, x, across the sphere parameterized by, and here's our parameterization given to us. And there's a few hints that kind of it helps us out with. So it's going to be quite nice, along with some integrals here, which I don't really understand at this point how they get used, but maybe later on this will become useful to me. All right. So again, anytime that it says flux, this is going to be a surface integral here. We could go ahead and plug in our specific vector field, z, y, x. Now, there are two different ways of evaluating out this ds, right? And we saw those in the pre-class video. One of them, if you have an explicitly defined surface, and I'll jump back to this video here for us now, but if you have an explicitly defined surface, the equation's a little bit nicer, right? You just need to take some partial derivatives with respect to x and with respect to y, and there's that -1 in the z component. No. And then on the other hand, if you have a parametrically defined surface, right, you need to dot product that with plus or minus this r sub s cross r sub t. And that's usually a little bit more difficult. And so that's the situation that we find ourselves in now. And so let's go ahead, jump back here and try to solve this problem together. All right. So the first thing, well, we're going to be solving this parametrically. After all, it's given to us, the surface equation and all that sort of stuff is given to us parametrically, and we have some nice hints. And so I'm going to, first off, everywhere that I see a z, I'm going to swap in for my z coordinates, right? So we have our parameterization of our surface. We have an x coordinate, we have a y coordinate, and we have a z coordinate, right? So that's my x's, my y's, and my z's. And so again, everywhere I see a z, I'm going to put cosine of s. Everywhere I see a y, I'm going to put sine s sine t. And everywhere I see an x, I'm going to put sine s cosine t. I need to do a dot product with plus or minus, and this would be the r sub s cross r sub t. Now, luckily, that's given to me here. So r sub s cross r sub t, that's going to be my normal vector. Remember this dot ds, this is going to be with a normal vector. And so, well, we can go ahead and copy that. Sine squared s cosine t, sine squared s sine of t. Running out of room, I probably will cheat here using my technology. Just going to move that over. And then we have sine s cosine s. Sine s cosine s. And then when we do this parametrically, right, we're going to have ds dt. So we're going to be integrating with respect to s and with respect to t. Now, a common mistake that I see in the web work homework, because there are a lot of sines and cosines here, is that sometimes people write s when they mean t, or they write t when they mean s, right? And so that's one thing to be paranoid about and make sure that you have correct, especially for the web work homework, but also for the quizzes and the exams. All right, now in order to get this entire surface, right, we are going to be, right, our s's range from 0 to pi, and our t's range from 0 to 2 pi. Again, kind of t's are taking the place of theta, s's are taking the place of phi. So this is how we get our entire sphere. Now, we need to evaluate out our dot product, but then we also need to choose a plus or a minus here. Now, this is where I want to emphasize something very important, because I've seen some people, they get really hung up on this plus and minus business, right? And they say, oh, I don't know what it is. I'm not 100% sure. And so they just stop right here, right? And I want to emphasize that it's much, much better, kind of partial credit wise and everything, to just choose something and keep going, get as far as you can, sort of deal. And at worst case scenario, you may be off by a negative, right? And it is what it is, sort of deal. But you're going to get a lot more partial credit if you go ahead and you just try something, rather than if you stop here and kind of just give up. And so let's go ahead and pretend for the time being, right? Say I don't know. If I saw this on a quiz or an exam, right, I may just say, well, I'm going to temporarily choose the positive for the time being, see what that is, right? And then I can think about the orientation after I've done all of my other problems, right? If I want to come back to this, if I have extra time, right, I can mess around and make sure that that was correct. And if it's not, right, then I can just change it to a negative, and that's going to make your answer negative. So if I do all this work and I get an answer of 5, right, and you decide afterwards, oh, I wish I would have had a negative there, well, then your answer should be -5, right? That's the only thing that it changes. And so it's a pretty easy thing to kind of, at the end, go back and fix as needed. All right, so I'm going to choose positive for the time being, just kind of pretending. And then we'll do this entire problem, and then I'll showcase like how can we go and check. So, all right, 0 to 2 pi, 0 to pi. Let's go ahead and do our dot product here. So when I evaluate out my dot product, let's see, my first coordinates here, this is going to be sine squared s, cosine of s, cosine of t. And so again, kind of sometimes I see people write accidentally like cosine squared t or something like this. No, one's cosine s, one's cosine t, right? They're different. All right, moving on to my second coordinates here. We have sine s, and looks like there's 3 of them. So sine cubed s, and it looks like we have 2 sine of t. So right, sine squared t. Sorry, excuse me. And then finally, for our last components, we have sine s, and there's 2 of them being multiplied together. So sine squared s, and then we have a cosine of s, and we have a cosine of t. And so in fact, it looks like this first and third component are actually the same. So you can combine these, of course, right? And when you add them together, you would just get two of them, right? So you could do something like that. So like components here, just multiply. All right, so there, move this over. It's a good second line. Now we need to kind of get into the evaluation of our integrals. So let's go ahead and do our S integral first. And so when I'm looking at this, right, this 2 cosine of t, that's along for the ride. I'm just integrating with respect to S here. And so if I was doing this, right, I would think about a U substitution. Maybe U would be equal to sine, and then du would be cosine. So when I integrate this, I'm going to have 1/3 U cubed. Of course, U is equal to sine of S. So this is going to be sine cubed of S. And you can double check, right? If you take the derivative of this, you should get back to where you started. All right, sine cubed S, right? This one's a little bit difficult. I don't know how to evaluate. I guess I should go back really quick, right? We're going to be evaluating our S integral from 0 to pi here, just as a reminder. Okay, but sine cubed S, I don't know how to evaluate that maybe so well. We'd have to do some kind of fancy trig work. But now is the time where we could go back up and we can notice that actually it gives us that if you're interested in an integral of sine cubed from 0 to pi, and in this case, it uses u, right? So it doesn't spoil if this is supposed to be s or for t or what have you. But if you're interested in the area under the curve of sine cubed from 0 to pi, right, that this ends up being 4/3. So that's very convenient for us. This is just 4/3. And of course, the t's are along for the ride. So if I was to go ahead and plug in for my first one, right, s's range from 0 to pi, well, sine of pi is 0 and sine of 0 is 0. So actually, this is just going to be 0 minus 0, aka 0. So this is just going to be 0 plus 4/3 sine squared t. I still need to evaluate out my t integral. And this one's not too bad. We could use a power reduction rule, which is on our formula sheet, by the way. But we do also have the second piece of information here, that if you want the integral of sine squared u du from 0 to 2 pi, which of course this is our range for our t's for 0 to 2 pi, that this just evaluates out to pi. And so this is going to be, at the end of the day, 4/3 times pi. And so that would be our final answer here. All right, so as promised, right, you can see that I can get quite far if I just assume some orientation, right, that I assume that this is going to be plus rather than the minus. But let's suppose that I wanted to spend a little bit of time going back and seeing, is this actually oriented outward? Because again, we want the outward flux. So I want to make sure that my normal vector is outward. And so in order to check this, what we need to do, and this is very similar to when we did this kind of back in 16.4, part B, when we were doing flux stuff, is that we need to choose a test point. So we're going to go ahead and choose a test point and see if at that test point, our normal vector is pointing inward or outward or what's going on. So, all right, I'm going to go ahead and choose a test point. Probably my favorite one is s equals 0, t equals 0. And the first question I need to know is, where am I on the sphere at that time, right? Because for instance, if I'm over here on the sphere and I end up getting a normal vector that's pointing maybe off to the right, that is outward, and I'd be happy about that. However, if I'm over here on the sphere and I get a vector that's pointing off to the right, now that's inward. And so I wouldn't be so happy about that. And so we really need to know where we are on the sphere or on our surface in order to tell if our normal vector is pointing inward or outward. There can be cases where, again, you get a vector and it really depend on where you are on the surface to know if that's pointing inward or outward. So we need a pretty good picture here. So let's go ahead. If I plug these things into my parameterization, that is, everywhere I see an S, I'm going to plug in a 0. Everywhere I see a T, I'm going to plug in a 0. And this will tell me where I am, right? I'll get an X, a Y, and a Z coordinate. So in order to get my X coordinate, I'm going to be plugging those things into my, that first coordinate there for the X's. So if I plug in S equals 0 and T equals 0, I'm going to have 0 here. Next up, for the y coordinate, if I plug in s equals 0 and t equals 0, I'm going to have, well, again, sine of 0 is going to be 0. So it doesn't really matter what else there is. So again, I'm going to have y equals 0. And then finally, if I plug this into my z coordinate, I'm going to have cosine of 0. That's 1, right? And so I'm going to be at 0, 0, 1. So all that to say is at this point, I'm going to be at this north pole here, right? Haven't gone any in the x direction, haven't gone any in the y direction, and I've just gone one up in the z direction. So if I want to, I can include my axes here just so we can really see that. So here's my x, y, z axes. All right, so I'm here. So that means if I get an answer that's pointing upward, a normal vector that's pointing upward, I'm going to be happy with that because that's outward. On the other hand, right, if I found out I was at the South Pole here and I got a vector that's pointing upward, I wouldn't be so happy with that, right, because now that's pointing inward. All right, so now let's go ahead and check out our normal vector. So again, our normal vector is given by this cross product of our tangent vectors, our r sub s cross r sub t. And so if I go ahead and I plug these things in, so for instance, when I plug in s equals 0, I get for my x coordinate 0, right? Because again, we have a sine squared s. In my y coordinate, I also get 0. And in my z coordinate, I also get 0. And so sadly, I knew this was going to happen. We didn't get a vector that's pointing either upward or downward here, which is kind of annoying, but sometimes this happens. And if that happens to you, right, we just need to choose another test point. And so I'm going to change up my test point slightly, and I'm going to choose one, maybe s equals pi over 2, kind of staying away from the north and south pole. The kind of the endpoints here is sometimes a good thing. Sometimes you get wonky values at your endpoints. Okay, so let me show you now a good one. All right, so going back, I need to figure out where I am. So if I'll erase these really quick. All right, so if I plug in, and again, we're doing this into my XYZ parameterization. So I'm looking at these things here. If I plug in sine of pi over 2, that's my s, and cosine of 0, that's going to be 1 times 1, that's 1. If I do the same thing here for y, so sine of pi over 2, sine of 0, we're going to have 1 times 0 is 0. And then finally, in my z's, if I plug in cosine of pi over 2, that's my s value, I get cosine of pi over 2 is 0. So in this case, I'm over here. I've gone 1 in the x direction. I haven't gone any in the y and any in the z. Okay, so I'm really hoping for a vector that's pointing, in the positive x direction here, rather than one that's pointing in the negative x direction, right? Because that would be outward in this case. So let's go ahead and check our normal vector. And so now again, I'm going back over here and I'm plugging in everywhere I see an s, a pi over 2, and everywhere I see a t, plug in 0. So, okay, sine squared pi over 2, that's going to be 1 times cosine of 0, that's going to be 1. Sine squared s, that's going to be 1 here, times sine of 0, that's going to be 0. And then cosine of pi over 2 will be 0. Sine of pi over 2 is 1. So again, you get 1 times 0. And so we get the normal vector 1, 0, 0. So that is, it's pointing in the x direction, positive x direction by 1. It's not going any in the y direction or any in the z direction. And so yes, this is outward. And so that was the correct decision to make all along. You can see that this took a decent amount of time, right, to figure out that orientation. And again, if it had been wrong, if we had done this in the opposite order and we wanted to choose the negative, then the only difference down here would be that this would be negative 4/3 pi. And so again, the big thing about the orientation when it comes to these is that if you are at all hesitant or whatnot, just choose one option, get as far as you can with that. And then at the end of the quiz, end of the exam, if you have any time, you can come back and figure out the plus and minus. I've seen plenty quizzes and exams, the grading rubrics though, if this was like a 10-point question on the exam, if you did all of this here, you might get, heck, even 8 or 9 points sometimes. So not to say that's a guarantee by any means, but still, if you were to stop way back here because you say, oh, I don't know what the orientation is, let's just stop sort of deal, right? You've missed out on a lot of points that you could have gotten. So, all right. Well, I hope that this has been useful. Thank you guys for watching. As I said in class, right, I knew that this was going to be kind of a very long class, and I didn't really have much hopes of getting through all of my notes, but I hope that this has been useful.